Yeah. Okay. So we've sort of split up the slot into a presentation from me and then a presentation from Ahu. So our topic will be materials, in particular packaging, plastics, and their impact, and then how we look to nature for solutions and inspiration. And so my name is Guilhem. I'm a research fellow at the University of Manchester. I did my PhD in materials, in particular in plastics. So you'll see a lot of that emphasized throughout my slides. And at the beginning of this talk, I just want to focus on the impact of plastics on our sort of society and our environment. So we first have to start to acknowledge that plastics, which is a really important category of materials, have a lot of benefit to us as a society. And that's primarily because they're very durable, they're very lightweight, and they're non-expensive to make. And these properties lend them to being really versatile. So you can see them in a variety of applications just because from sort of the same types of materials, the same plastics, you can engineer them to fit a lot of different applications. And so I'll show just a few examples in this slide. The top left being packaging, which we're sort of going to focus on, but there's a lot of advanced materials. So in the automotive industry, as we just talked about a little bit, in terms of engine components and metal, that is often accompanied by lightweight sort of parts in an automotive or other travel application. You have even more advanced materials, I would say, that protect our lives and limbs when we're, in the army or military. And that goes all the way back down to sort of the more consumer toy application where you have these little Lego men, which is a bit of a pun because they're actually building something themselves, but they themselves are an interesting example of plastics use. They're very important in construction and then in agriculture and also in medical applications. So you have here, I'm just showing, this is an intraocular implant. So it's something that is implanted into somebody's cornea that can help them regain some vision. And then of course we have more, perhaps more frivolous applications or more aesthetic applications. I don't know if anyone's familiar with the concept of bejeweling jeans, but this is what it looks like when you have little plastic rhinestones and you adorn denim with them. So the applications range from sort of critical to sort of, aesthetic or maybe more trivial. We use them in all of these applications, and I think it's important to recognize that the way in which we've grown to use plastics and depend on them has created an unsustainable paradigm. And what I mean by sustainable, I'll just present what's become a classic definition of sustainability, which is meeting the needs of the present without compromising the ability to meet the needs of the future. And basically, the way in which we use plastic, we make it, we use it, and we dispose of it, does not really meet these criteria as well as it could. The first problem I'll talk about is in production. So I mentioned production, use, and disposal, and I think the main challenges in terms of plastic packaging and plastic use in general is really in the production and in the disposal. So we're going to talk about both of those in order. So this is a plot from a paper that has one of the coolest titles, I think, which is The Production, Use, and Fate of All Plastics Ever Made. This was published in 2017. It's quite a heavy-hitting title. And it has the plastic production over the years since 1950 split up into these different sectors. And you can see that packaging is in the bottom here, and it makes up the majority of plastic production. And the first sustainability challenge is, like I mentioned, the production of these plastics, which is growing exponentially. We're using more and more of them over time. And the way in which we make them is reliant on petrochemicals, that is, those chemicals that are derived from fossil fuels. And it takes over 1 million years for biomass to become oil. So by definition, the timescale on which we use these plastics is much less than the timescale that biomass becomes oil, and therefore we're using a non-renewable resource. So I think the first material science challenge in the field of plastics, and in particular in packaging, is we need to develop efficient approaches to turn biomass into old and new plastics. And I say old plastics because there's a reason that the plastics that we use have stuck around for so long, which is that they're very good at doing what they do. So it's okay if we develop new materials, but I think we'll never get away fully from all of the commodity plastics that we use today. Right, so the other concept that I've already touched on is the fact that plastics are very durable and the fact that we use them over a short time frame. And that conundrum, or that juxtaposition, is really the durability versus the functional lifetime. And packaging has it's called single use, and that, or a lot of packaging is called single use. And that really translates from sort of this big picture view into the concept that plastic packaging just has the shortest functional lifetime out of all of these other sectors. When we look at sort of the volume of packaging that exists, this is data from 2016, so it will certainly have increased, but at the time it was about 78 million tons of plastic packaging that was produced annually, and this is on a global level. And this materials flow diagram gives you a sense of where this plastic ends up. And so on the top part, there's these sort of circular loops, or there's a circular loop. That is the recycling process. And so only 14% is collected for recycling. 4% of that is actually lost in the process. 8% of that cannot become, or 8% overall cannot become a similar value material, which is so it gets downcycled into something that's lower value. And then 2% overall of plastic packaging at the time was getting made into new plastic packaging of similar value. That leaves quite a bit destined for another fate. And those other options are incineration, landfill, or mismanagement, i.e. environmental pollution. So as you can see, 14% ends up incinerated, 40% in the landfill, and 32% in the environment. This is, again, a global level. The situation in particular is a little different in the UK, but it just shows you sort of a good ballpark for each fate. And I think the first thing to notice is just that the primary recycling infrastructure is inefficient. So most plastic ends up elsewhere. This is a large majority ends up in these three other fates rather than in recycling. And unless it's recycled or incinerated, plastics will persist either in a landfill or in the environment for hundreds of thousands of years, hundreds or thousands of years. The consequences of this sort of paradigm, this is the linear paradigm of our plastics use, is that we have environmental pollution, we have increasing amounts of waste that have livable land consequences, so social consequences. And then of course, we're losing this material to a non-circular fate. We're not reusing it in a way that's recovering the value that's in that plastic waste. And so I think the main challenge is or the main challenge for end of life is basically developing better recycling and also redesigning materials so that if it makes sense for the application, to design them to be degraded after their functional lifetime. And so these, I think, are the two material science challenges around end of life that will really improve the sustainability of our plastics use. Okay, so now some slides with a bit more interesting pictures, or perhaps less shocking pictures, which is related to how we look towards nature for solutions or inspiration in plastic material design. So the first thing to point out is just animals have a wide variety of very impressive materials. And so these are pictures I took while I was traveling in South America. And on the left-hand side, there's a beetle with a very hard exterior shell, which is sort of a marvelous material in and of itself. And if you pay attention in Ahu's talk, you'll actually see a beetle pop up somewhere. On the right-hand side is a beehive that I saw on the side of a building that was quite terrifying at the time. And on the inside of that beehive, I know that there's a soft wax beehive structure. And I think what's interesting to point out about this right-hand side is just, it's a very hard material on the outside and a very soft material on the inside, and they've somehow adhered the whole thing to a wall. So I think it's interesting to point out just the diversity of materials that these single animals make. So from that, and other examples such as this mollusk, this mussel, we can sort of realize the potential of materials and try and understand how we might design our own. So this example demonstrates sort of the ability of marine animals to stick to surfaces. And in particular, I'm showing a mussel, which is forming a very strong bond, one so strong that it can hold up the rock that it's stuck to. And the way that it does that is by secreting a glue from the inside of these little threads, which you could consider arms, if you like. The only part of this diagram that really makes sense to us anatomically is probably the foot, although it doesn't look anything like our feet. But if we can sort of understand the chemical reactions going on at the end of this thread in what's called the plaque, or what makes up this entire byssus, which is this whole hair-like structure, maybe we can get a better insight into how they make this glue, and then we can design our own underwater glue that's bio-inspired from this mussel. I'll show one more example and then move on to Ahu's talk, which is the example of shark skin. So this whole concept of marine animals sticking to surfaces is called biofouling. And there are some surfaces out there in the ocean that don't have a lot of animals stuck to them. One example is shark skin. And the question is, why does it resist biofouling? And if we can understand that, perhaps we can design materials to do the same thing. And the answer to that is that if you look at shark skin very close up, you'll see it's made up of these scales that have a ruffled texture. So these scales have a very rough surface, and that rough surface and the constant motion of the shark makes it so that these small animals, which when the mussel stuck to that surface, it was actually a baby mussel. It was very small. And when they try and find a spot to settle, they don't like rough surfaces. So this in and of itself can be considered nature's version, but we have ways in science of sort of replicating those features. And so this is an example where scientists created a surface that essentially is a pattern where you have these little ridges and valleys on sort of a similar length scale to the scales on a shark. And so this concept of design can be considered bio-inspired design. And I'll transition now into Ahu's talk that will give a bit more insight into the way that process and other examples and even how we can apply that to something like packaging. It's all you, Ahu.
Hello. Now I will try to give you a story around how we can design new materials and production protocols based on using nature and biological world as an inspiration. So with the power of new characterization techniques, we have more insight on how the biological world and how the natural material constructs are coming together. So that gives us a very good inspiration point for developing new advanced materials. And in Guilhem's talk, we saw some marvelous examples of how these materials come about. And I think that entices our curiosity, how this is coming about. And we try to really understand and explain how that sticking function, how sliding functions, or how a sunflower is following the sunlight is coming about. And when you look around nature, you will see that every function is optimized in a certain way. And that comes from the billions of years of evolution, obviously. And you can say that nature is the ultimate materials engineer or ultimate engineer. So we can take an idea or find a engineering challenge, and you can biologize or find a biological analog for facing a natural system that face similar challenge, and try to match and discover the method or discover how nature approached to it and create an abstract concept and try to repeat this over and over again, because in every experimentation, there's an element of things may not work the way you planned it to be, but you will continue to try to do that. One thing I find fascinating about nature is we see all kinds of functionalities built into very simple organisms and very simple structures, actually. And as I said, nature managed to go into every sides of engineering protocols and processes. So, and interestingly, nature has a very narrow material palette, and all these material palettes, as opposed to our material palettes we use on our everyday lives, is very limited. We have proteins, sugars, and mineral matter, and these are all very abundant materials based on carbon, but the most basic forms are of carbon. Sugar, proteins are a little bit more complex, and as you go higher in the evolution scale, the constructs of the building blocks get a little bit more complicated. Well, when you look at the ways we use the materials, fossil-based, these are taking the majority of our production, and we are not putting as much emphasis on the renewable or degradable replacements for that. But as Guilhem put it in a perspective, we need to change our habits, and there are many implications of how we should do that. And we have targets, very solid targets to meet. By 2025, we need to be eliminating single-use packaging materials by recycling or finding compostable alternatives. And we need to make sure 70% of the plastic packaging is effectively recycled and composted. And again, by 2025, 30% of average recycled content across all plastic packaging. So we have a very big job to do. And in Manchester, we are both, Guilhem and myself are working in the same floor, Sustainable Materials Innovation Hub, targeting for these challenges. So classical polymer engineering, polymers are all the materials that is making up all the packaging materials, as well as other commodities, as you've seen. Works in a way that, yeah, we have you have a moldable material, you heat it, you consume energy, or you use a solvent-based dissolving method, and you put it into a shape, and that shape will give you functionality. When you look at nature, it is a different way of making things. Legos come into place again. So nature builds these building blocks, and what we say, those building blocks come together to create a certain function. And nature does this as a build-up method, not like top-down method we just seen in the way we practice in our engineering solutions. So bottom-up way of making things are very energy efficient, and we can rely on the chemically abundant elements like nature does. And the biggest difference in my point of view, and I hope you will agree after my talk, is multifunctionality is a key concept in nature. So one thing that you see in the beehive, for example, was giving that pattern to save space and accommodate the most for the extracts of the honey, but also it was sticky on the wall. And it is probably light enough at the same time to keep its weight support on the wall as well. So there are lots of multifunctionalities and optimizations comes into place just by using one material. So what we can do in our practices is exactly that, actually. That will save us time, save us energy, and save us material consumption as well. And what it does is material palette is the same, but their shapes and patterns change to give those functionalities. So there's a very key element there. Going back to packaging, nature also offers very good solutions for the packaging applications as well, right? All the fruits come with a skin, come with a peel. So that is to protect the inside and the seed mostly. So those are the two parts that we can see. In this pollia condensata, it's an iridescent one. So multifunctionality, it is going to do the dissemination as well as it is attracting the birds or other animals to pick it up and take it somewhere else. So it can disseminate as much as it can. So this is a survival technique in the sense of orange peel. The smell is another function embedded inside the material. Coconut shells, the fibrillar structure is very useful, very hard, giving us a lot of ideas on how packaging should be. And mantis shrimp, one of the strongest materials of all time, is to create a skeleton for the shrimp to make a very, very strong, tough exterior, maybe going back to military applications we shown earlier. So all these materials come from a biological source. It is polysaccharide, actually. So when you look at the life cycle of the polysaccharides, the shrimps or the trees, we have the polymer we extract from the prawn shrimps is called chitin, and the polymer we extract from the wood is called cellulose. They have this sugar structure, and they are making those polymers long chain of molecules, and those long chains of molecules are actually making fibrillar structures. So what we do is we extract those fibrils, and we are combining them with different kinds of particles or different kinds of plasticizer, other natural products as well, to give barrier layers as well as other properties. Multifunctionality is a key. And then we apply them on surfaces, or we can process them as films. And this is not our products, but potential applications is fibrillar constructs, food packaging, single-use applications. And the beauty of it, these bioplastics, you can compost them directly and they will go back to their food, their chain of chemical cycle, and go back to being carbon-based products and water and ammonia. So they will go back to making new cellulose, new chitins. There are many startup companies as well as very known producers. So what is our job here is to really understand the consumer habits and the finances that goes into it, because we need to really balance it out, because we have a habit of going for the easy thing, convenient thing, but we can replace these easy and convenient things with biopolymer replacements very easily, and the solutions exist. And we are also keep innovating in this area as well. So one of the things that I want to very briefly touch is actually how you approach the menstrual care can be changed as well. This is a study that we are doing at Manchester right now, is to extract biopolymers from prawns directly to make transparent and strong films that are stretchable. So you can really replace the material itself. And the beauty is, this is the prawn itself, showing that how that laminar structure is giving you very tough exterior. By producing it in a mild way, you can actually produce a very similar film and reconstruct the prawn shell with some plasticizer in it, so it can be also stretchable at the same time. So the future of materials is going to be looking much brighter than what it is looking like right now. We need to apply some principles with it. We need to rethink our material palettes and the platforms, what we use, and not only the materials themselves, but what kind of energy cycles they go through as well, because that it actually is to big players that we need to design our strategies around. We also need to reduce, especially the non-recyclables and non-compostables. So as consumers, we are scientists, but consumers at the same time. So we need to make the right decisions and try to reduce as much as we can. And again, consumer end solutions, reusing the plastic, but petroleum-based plastics, where we can find another use, we should use them. And recycling is a new catalyst innovations or new polymer innovations, actually, to reconstruct these, break down the polymers and reconstruct them again. So, and really giving solutions that is much more efficient than 2% of those polymers goes to recycling routes. We need to do much better than that. And obviously, with the integration of the biopolymers to these petroleum-based ones, or just pure biopolymer-based products can be really good alternatives for compostings. So that's also materials discovery, because we know that nature optimized it for their functions. We need to optimize now these polymers to our functionalities. And as I've shown you, it's very easy to get inspired and innovate if you have the right examples in front of you, and nature offers plenty of that for us. So with that, I thank you. And yeah, my name is Dumanli-Parry, and yeah, if you have questions, we will more than welcome to take them.
That was absolutely inspirational. Thank you so much, both of you, for those. And yeah, it was both talks sort of like shown sort of nature really is a fantastic inspiration for materials research. Has anyone got any questions at all for either speaker? Okay, yeah, for both of you, Reid, do you think that sort of bio-inspired plastics will eventually replace sort of conventional plastics, and sort of how long do you think until that would be the case? I know sort of
you want to go first?
Either of you.
Well, if I start, maybe Guilhem will correct me if I'm wrong. Well, there are some solutions available, and they are already at the very high technology readiness level. They are in production stage. I think what we can do is to specifically go for those alternatives. And some companies like Coop, the way the single-use shopping bags are changing now, they are offering the compostable alternatives. So it is already penetrating to the market, but I think it's a slower buildup than what we expect to replace. And some of the things that there's a big hype about these biomaterials or recycled alternatives, but maybe the technology needs to catch up to offer large-scale solutions much faster as well. What do you think?
Yeah, I'd agree with that. And I think the important I think there's two important things I'd add, which is the first is that the rate is limited in part by the infrastructure that we're building to deal with the waste. And in part, that also has to do with anticipating consumer behavior, which is a really important dimension we didn't touch on. So those compostable bags that Ahu just mentioned, I heard a story about how because they're so easy to break, people were doubling up or tripling up on the bags, and that can actually change their compostability, right? So we have to sort of balance our expectations with the reality of what consumers do when things are released and the infrastructure that we have at the end of the day to deal with it. And then the other thing I'd say is just that in particular, I think Ahu's answer is framed in packaging, which I think is one of the best applications for these bio-based and in particular bio-based degradable plastics. They're not always synonymous, but and it's important that in applications where it makes sense, we really push for those solutions, but in other applications, it may not. So, you know, in construction, I don't think we'll ever really replace construction plastics with bio-based degradable plastics because it wouldn't make sense. And that's perhaps a pretty obvious example, but there's a lot of gray area in between single-use food packaging, which has food waste on it, which should probably be composted because otherwise we'd have to clean it and recycle it. And then construction, which, you know, there's a lot of space in there to have nuanced debates about where it does and where it doesn't make sense. I'd say another good example is perhaps in agriculture, you know, when we have plastic, which improves yields by, you know, controlling weeds and reflecting sunlight and keeping moisture in. But then you have all this material on the field, on the agricultural field, and it's very hard to recover and for it to be cleaned. And so that's another great application for these bio-based and in particular biodegradable materials.
Awesome. Well, yeah, no, thank you both so much for your time.